Hello, everyone. Thank you for attending this talk. Location information is critical for many navigation and tracking applications. GPS is the de facto standard that enables the wide adoption of these applications. One serious problem with GPS, however, is that it is shown to be vulnerable to signal spoofing attacks. This is because of a lack of authentication in the standard and also because the power level of the real signal is quite weak, in the order of nanowatts. As such, a receiver has no way of differentiating between real and fake signals, and this enables an attacker to force a receiver to lock onto fake signals by transmitting these signals at a slightly higher power. There is significant research in the area of GPS spoofing that shows how serious this vulnerability is. Using cheap and readily available software-defined radios, it is currently possible to change the course of a ship or even force a drone to land in a hostile area. There are many other implications, such as the possibility for a criminal to escape by spoofing their location, or it can be something as simple as cheating in a game like Pokemon Go. So, inertial navigation systems, or INS, have been considered as a popular complementary system, especially in road transportation. Many big companies like VectorNav, Honeywell, and Navtech have deployed GPS INS-based systems for improved navigation and tracking of vehicles. Even though sensors are inherently noisy and drift over time, these constraints in the road networks themselves still allow for better navigation applications. Moreover, these sensors are resilient to spoofing and jamming attacks, which makes them very attractive for use in tracking applications. This work is one of the first to study the security of GPS INS-based on-road location tracking systems. We answer the questions such as, can a driver of a vehicle carrying high-value commodities spoof their assigned route and travel to destinations without detection by a monitoring center? If this is possible, how far can they actually deviate from the intended destination? Another question could be, can a parole with a GPS INS ankle monitor spoof their location and travel to routes without detection? We study the security of these systems by building algorithms that generate thousands of routes to different destinations. These routes are generated such that they completely evade GPS INS-based location tracking systems. During the initial reviews of our paper, one of the reviewers commented about the difficulty of real-time spoofing due to variability in traffic conditions. That prompted us to implement the first real-time integrated GPS INS spoofer that accounts for traffic fluidity, traffic lights, and stop signs. This spoofer dynamically generates spoofing signals based on the real GPS signal, and it works quite well in the real world. So in this attack, the goal of an attacker is to spoof the location and drive a route that is different from their intended route. This attacker first downloads a road network of their city and then constructs a graph from this network. Next, whenever the attacker wants to spoof their destination, they give their source and destination as input to an attack algorithm. This algorithm first generates a set of spoof routes that are alternative routes an attacker can take to drive to the intended destination. The idea behind these spoof routes is to find routes that have a high likelihood of topologically similar routes to other destinations of the city. Next, the algorithm uses these spoof routes as inputs to generate hundreds of escape routes. And these escape routes are the ones that the attacker will take to drive to different destinations without detection by a GPS INS tracking system. Finally, the attacker chooses a pair of spoof and escape routes to reach a specific destination, and they feed this pair to a real-time GPS spoofer to execute the final attack. Here is a more visual representation of this attack. In this specific case, the attacker is expected to travel from the green marker to the red marker. And the green line here shows the shortest route between these endpoints. However, when these endpoints are given as input to an attack algorithm, the algorithm computes a set of spoof routes that are represented here by the red lines. Now, the algorithm uses these spoof routes as input to generate escape routes, and two of them are shown here by the blue lines. So you'll observe that these blue lines, that is the escape routes, end at a destination different from the red line, that is the spoof route. However, they are very similar in terms of turn angles and curvatures. So using this technique, an attacker can generate hundreds or possibly thousands of escape routes to different destinations of the city. In this specific case, you can see that the attacker would be able to cover almost a quarter of central Manhattan. So moving on to our technique. I'll explain the graph construction first using an example road network. In this specific network, the edges that are represented by the red dots form the graph, the intersections form the graph edges, and they contain the turn angle with the connected vertices. The road between these intersections form the graph vertices, and they contain the road curvature and the travel time between the endpoints. This specific road network translates to the graph that is shown. So previously, I had mentioned that an attacker can travel using spoof routes that maximize the likelihood of finding topologically similar routes to other destinations. This can be done by scoring and sorting routes based on their probability of occurrence in other sections of the graph. For example, if you look at the turn and curvature distribution of Manhattan, you'll observe that the probability of 90-degree turns and straight roads is much higher than the others. Intuitively, a route that has a higher likelihood of spoofing would most likely contain all 90-degree turns and straight roads. In fact, this is true for all major cities of the world. I'll discuss these cities during evaluation. However, here you'll observe that all of them have a majority of 90-degree turns and straight roads. The algorithm for generating these spoof routes is an extension of the depth-first search algorithm. These extensions are very specific to the attack. So I'm going to abstract away from the technical details, and they are all described in detail in our paper. However, at a high level, this algorithm filters all the routes that are unlikely to be taken by a regular user to reach a specific destination. A good example of filtering could be a route that keeps moving south when the destination is actually towards the north. The algorithm scores all the remaining valid routes using compound probabilities based on the turn and curvature distribution of the city, as I described previously. In the end, this algorithm selects the top scoring routes as the spoof routes, and they are given as inputs to generate the escape routes. In our evaluation, we chose the top 100 spoof routes in order to perform simulations for thousands of different routes. However, this attack performance can be significantly improved by choosing many more top routes. A question that now arises is, now that we have a set of spoof routes, how do we use them to generate escape routes? This can be done by exploiting the inherent noise that impacts accelerometers, gyroscopes, and magnetometer sensors. For this work, we use an open data set of sensor recordings for 140 routes and calculated how much this sensor data deviated from the true expected values. This slide shows the accelerometer bearing turn and curvature errors calculated from the sensor data. And in our algorithm, we set the error threshold to 75 percentile of these values. This essentially means that the attack algorithm uses much more accurate sensors than those used in this data set, and those typically present in most modern smartphones. The escape routes generation algorithm must ensure that the output escape routes are topologically very similar to the input spoof routes, while also accounting for the fact that these routes may contain different curvatures, turn angles, and route distances. And the filtering here ensures that the error, all the differences are within the error thresholds that were defined previously. Again, you can read about all these techniques in our paper. Moving on to the real-time spoofer. So I must emphasize that even though we built this system for road networks, this is a generic system that can be used across different scenarios impacting drones, ships, aircrafts, etc. In our knowledge, this is the first implementation that accounts for varying conditions such as traffic fluidity, traffic lights, and stop signs. The implementation of this spoofer is not trivial because algorithms must be implemented that can compute locations in real time and transmit them quickly before a GPS lock is released. The way our spoofer works is that it maintains a mapping of spoof and escape locations. On receipt of the driver's real location, it efficiently computes the location and bearing to spoof, typically within 5 milliseconds, and then parallelly sends the location to a GPS spoofer and the bearing to a magnetometer spoofer. Let's look at a video demonstration of this spoofer. So the phone on the right shows the true location, while the one on the left shows the spoof location. And on the very left is our implementation of the GPS INS spoofer. So now this first scenario would show a synchronized turn between the true route and the spoof route, and you will observe that both of them turn at exactly the same time at different locations of the map. So now this other scenario would show a synchronized stop between the real and the spoof route, and you will observe that both of them stop at exactly the same time at different locations. Eventually, the destination that is shown by the true route and the destination shown by the spoof route would be two different locations on the map. And in this specific case, they are about 1.5 kilometers away from each other. Moving on, we evaluated this spoofer by driving 10 routes in Boston. During these routes, we observed that we did not lose a lock even once, and the maximum delay in calculating the location and bearing to spoof was at most 60 milliseconds. Moreover, all the sensor errors were within the error threshold that were defined, which suggests that this spoofer works quite well in the real world. The attack algorithm was evaluated using simulations in 10 global cities. These cities were chosen as they are all major logistics hubs, and they represent diverse road networks. For example, Manhattan and Chicago represent grid-like structures, while London and Paris represent high variability in turn angles and curvatures. For each city, we generated 1,000 routes using random residential and office locations. This slide shows the maximum displacement an attacker can achieve for every route in simulations. And here you'll observe that in grid-like cities like Manhattan and Chicago, about 50% of the routes have a displacement higher than 10 kilometers. And 20% of the routes have a displacement even higher than 20 kilometers. In the majority of the other cities, about 10% of the routes have a displacement higher than 10 kilometers. In all these cities, there are several routes with displacements even as high as 30 to 40 kilometers, which is significant deviation for an attacker from the intended destination. This second evaluation metric represents the amount of area an attacker can cover, provided they are willing to walk about 50 meters from the parking location. We define the total area of coverage as a circle where the source is the center and the Euclidean distance to the destination is the radius of this circle. And the area of the escape destinations are calculated using Monte Carlo simulations. This result shows that in cities like Manhattan and Chicago, even for routes as long as 10 kilometers, it is possible for an attacker to cover about 8 to 10% of the total coverage area. Given that an area of a circle increases quadratically, 10% is actually a significant area an attacker can cover using this attack. Finally, the countermeasures. We propose a secure routes algorithm that gives comparable performance to using military-grade sensors without deploying any new infrastructure. The way this algorithm works is that it essentially reverses the scoring function of the spoof routes generation algorithm. As such, it produces a set of routes that have a low likelihood of spoofing, and it chooses one specific route as a secure route that outputs the least number of escape destinations. This slide shows the results of the evaluation for this algorithm using the same routes as simulation. And here you can observe a significant reduction in the attack performance. Therefore, we contend that using our secure routes algorithm alongside more accurate sensors in the future, there is a potential to completely mitigate this threat. Thank you, and I'm ready for questions.
So, name and affiliation, please.
Mike Brotzman, Department of Defense. It seems that this, again, is works best in cities. Do you have any metrics of what road density you need before it starts breaking down?
So it doesn't really work well in cities or a rural area. What depends, like what makes this attack work is the kind of the road structure. Like for example, if you have some structure where there are a lot of 90-degree turns and straight roads, then this attack is going to work quite well. It doesn't matter if it's a rural network. In fact, if the blocks are much further apart, that gives the like the error in the accelerometer increases further, which would make this attack work even better in that specific scenario.
Any other questions?
Thank you for the talk. It was really interesting. My name is Daniel from University of Pennsylvania. I was wondering, so this all depended on the fact that you could spoof the GPS coordinates. This is maybe a bit tangential to the work, but what do you think is the feasibility of having the GPS signals be signed? And would that allow you to have like very secure GPS that would...
So I mean, there are military GPS which have some cryptographic mechanisms to protect them. In case of such GPS, then yeah, I mean, I don't think this attack is going to work because this relies on the fact that these GPS signals can be spoofed, yeah, which is pretty much all commercial GPS applications out there. Yeah.
Any other questions? So you mentioned your potential defense. Do you think it's ready to be deployed, say in like ride-sharing apps or things like that? Or are there further hurdles that you have to get over first?
Yeah, I mean, one disadvantage of this system is that it's a probabilistic system. Okay, so I mean, you cannot guarantee that the countermeasure would protect against all possible scenarios. So yes, I mean, this is definitely a good system for deploying now, but there must, like we are also looking at certain techniques that can be improved to make it foolproof. I mean, like, just not make it possible in any specific road network.
All right, let's thank the speaker again.
Thank you.